So welcome back for the second lecture of this week. So in the last lecture we were discussing bit-to-bit decoding for HMMs, and in the end we discussed the problem of learning the parameters of HMM. And we said that when the labeled data set is available, we can simply estimate using maximum likelihood estimate, okay, by the labeled data set. But if the labeled data set is not available, then how do we actually learn the parameters of the system? And we said we will be using some sort of expectation maximization algorithm, and in this particular case this is called the Baum-Welch algorithm. Okay. So Baum-Welch algorithm, as I was saying, this is a well-known EM algorithm to estimate the maximum likelihood for the parameters of the HMM. Okay. So what are the parameters of HMM that you want to estimate? Okay, let me just formally define them, and then we will see how do we estimate them using Baum-Welch. So in the HMM model, so we have a hidden state at every time point and an observation variable. Okay, so here I am using capital XT to denote the random variable, that is the hidden state, and capital YT to denote the observation variable. Okay. So both xt and yt can take many different values. So for our part of speech tag case, each xt can take one of the part of speech tags, and each yt can take one of the possible words. Okay. So this is my hidden variable, hidden state xt, and the observation yt. The parameters are a, b, and pi that we discussed last time. What is a? So a is my state transition matrix. So given that the previous state was I, what is the probability that the current state will be j? Okay. So here the t as such does not matter. What matters is that the state j occurred after state I at any given time point. Then I have the parameter pi, that is what is the probability that this particular state starts the sequence. So probability of x1, that the first state being the ith tag, that is my pi I. And then thirdly I have the emission matrix, so where the entries are what is the probability of observing this particular word or this observation given the current state. Okay. So this I am denoting like bjyt. At the state j, what is the probability of emitting the observation variable or observation yt. So these are the three set of parameters I have to learn. So now what is given to me? Okay. So I was saying that we are given the corpus, not labeled, but the word sequences are given. So this can be seen as my observations are given, different sentences are given. I know what are the different words occurred in the sentences. So I can say that I am given a set of observations in data. Okay, so here I can say that I am given a set of observation sequences, that the first observation was the word y1, then y2, up to some yt, where yt denotes the end of the sentence. So I am given a set of observation sequences, and my aim is to find out the optimal set of parameters theta that maximize the probability of this observation. So these observation sequences. So that's where I am using Baum-Welch algorithm. Find out what are the optimal set of parameters theta that will maximize the probability of likelihood of observing this observation. So that's why I am using expectation maximization algorithm. So what is the main intuition of EM? So idea would be, I want to estimate the parameters a, b, and pi. So what I will do, I will start with some random initial probabilities for all these parameters. I will initialize them with some random values. So I have all these probabilities. Okay. Now using this initial values, I will try to find out what are the probabilities of various state paths. So on a given sequence, what is the probability that a particular state would have occurred given these parameters? So, once I have obtained the probabilities of different state paths or different states at different point, now I got this probability. I will use that again to compute to re-estimate my parameters. So, I will get started with theta 0, I get some theta prime. Okay. Now, I will again use the theta prime to compute my state paths probabilities, again use that to recompute my parameters until it somehow converges. Okay. So, this is my iterative algorithm. First, use some parameters theta to get some likelihood on the data for the hidden variable here, that is the states. Once you have that likelihood or the probabilities, use that to compute my thetas. Okay. So what we are doing here? So, I am starting by choosing some initial values of the parameters a, b and pi. Okay. And then I have to repeat the following steps until convergence. What is that? Firstly, determine what are the probable paths. Okay. That xt minus 1, that t minus 1th point, I see the state I, at tth I see state j and so on. What is the probability of various state paths? Now, once I have these probabilities, count the number of times. So, what is important? Expected number of times, because we are only computing probabilities, we are not finding the actual paths. So, count the expected number of transitions aij as well as the expected number of times various emissions bj yt are made. Okay. So, using these state paths, can you do that? Yes, I know what is the probability of xt minus 1 is equal to I, xt is equal to j. I can use that to compute an expected value for aij, and this is what we will be doing. So, we will compute aij. Similarly, I already know the observation, so I can also compute some expected values for bj yt. What is the probability that I see observation yt for the particular state j? So, once I have computed this aij and bj yt, I will again estimate my parameters theta using these computed values. Okay. Now, I will go back in the loop. I have this theta, I will compute the probabilities of various state paths. Okay. Again compute aij, bj yt, and again compute theta. Okay. And I repeat that until convergence. So, now what is, so all these are interesting here. Like firstly, once you are given some set of parameters theta, it can be either the initial parameters or some intermediate parameters, how do you actually compute the probabilities of different paths? How do you actually do that? And for that we use a forward backward algorithm. That is the main concept of this algorithm. Okay. So, let us see what is this forward backward algorithm. Okay. So, in forward backward algorithm, we have a forward procedure and a backward procedure. Okay. So for explaining, let me just show it on paper once. So, what is happening? I am observing this sequence y1, y2, y small t, yt minus 1, yt. This is my observation. Okay. And correspondingly, so you can say this is y1 is equal to y1, first observation, y2 is equal to y2, and so on. Okay. And correspondingly, there are states. So, this is my observation, and then there are states. So, there will be some state xt, this is yt observation, this is my state xt is equal to I. It can be any of the possible states xt. Now, what do I do in this forward backward algorithm? I compute two different probabilities. One I call as the forward probability. This is the probability of observing y1 to yt and xt is equal to I given my parameters theta. So, this is my alpha t for the ith state. The probability that I am observing y1 to yt and at tth point the state is I given my parameters theta. Okay. y1 is equal to y1, y2 is equal to y2, yt is equal to small yt and xt is equal to I given a parameters theta. This is my forward probability. Then I compute a backward probability. What is that? This is the probability of observing this given this state. Okay? So, this is my alpha it and this is my beta it. That is probability that yt plus 1 is small yt plus 1 up to capital Yt is yt given xt is equal to I and theta. So, these are the two different probabilities that I store. So, what do you see here? So, I am taking just a state at a particular time t, a particular state I. Now, why do you actually compute this alpha it and beta it? How does that help? Now, I have these probabilities, I can simply multiply these alpha it times beta it to get the probability that I observe this sequence and the ith state. Okay? And to actually compute the probability of saying that at tth time point the state was I can marginalize it by all the possible states that can happen at time t. Okay? So, I can multiply sigma it, beta it and divide by all the possible sigma jt, alpha jt and beta jt to compute the probability of seeing state I at time point t. And that's how this forward and backward probabilities help me. Okay? So, we will see that in detail. So, right now just the formulation. So, I have this sequence, I divide into two parts for a given t. This is state I have the forward probability alpha it and a backward probability beta it. Alpha it is this particular sequence and the state, beta it is the ending sequence given this state, the previous state xt is equal to I. Okay? So, now, so this is my alpha it. Okay? So, now how do I compute these values of alpha it? I want to compute this for all possible i's and all possible values of t. So, this is a forward probability. So, I have to start with the first point. So, how do I actually compute alpha I1? Okay. What is that? So, alpha I1 from this equation which probability of observing y1 is equal to y1, okay, and x1 is I given theta. So, what is the probability of x1 is equal to I given theta? That is pi I. Okay. This is my pi I, and this probability would be emission from x1 from the ith state. So, this will be bi y1. Okay. So, this is how I will compute the initial one alpha I1 for all possible states I. Now, at some point of time, okay, at some point t plus 1, how will I compute alpha jt plus 1 given the previous alpha it I have computed? So, alpha j t plus 1. Okay. So, t plus 1 means the probability of seeing the sequence up to y t plus 1 and the state x t plus 1 is j. So, how can I compute that using the previous alphas? So, I have the previous alpha that gives me this. So, alpha I t at the previous time step I had some state I have the transition from I to j. So, times a I j and now I have the emission for the t plus 1th observation, that is bj y t plus 1. And this I can obtain from any of the previous states. So I have to sum over all the possible states here. Okay. So from all the previous states at the tth time step, I can be in state I have the transition probabilities and the emission probabilities for t plus 1, and that's how I can compute sigma alpha j t plus 1 from all the alpha ITs. So this is how you can compute your alpha j in a recursive manner, starting from alpha I1. Now what will you do for your beta j? Okay. So this is the backward procedure. So what is my beta IT? This gives me the probability of ending the sequence with yt plus 1 to yt given the state I at time t. This is my backward procedure. Now this I again compute recursively. In alpha j, I was starting from the first word, I was computing alpha IT. In beta j, because the backward procedure, I will first compute beta I capital T. T is the end of the sequence. And what will be beta IT? So beta IT would be probability of, so given that the tth point state is I having a sequence from t plus 1, but there is no word from t plus 1, so this will always be, so this will always be 1. This will be a null sequence, so this is always 1. Now I have to compute it recursively for all other beta I at time point t. Okay. So here I am going backwards. So you assume that you have computed all the beta j's at time t plus 1, and you want to use that to compute beta I at time point t. How will you do that? So this is very similar to what you did in the case of alpha. So we can see this. So this is beta j at time t plus 1, transition probabilities from I to j, and the emission probability for the t plus 1th observation, and you will sum over all the possible states at time j. So very similar to what you did in the case of forward procedure. So that's what you will do in the backward procedure for computing beta j in a recursive manner. Okay. So now you have a way that given the set of parameters, any parameters theta, you can compute all this alpha and beta. Okay. So all the alpha ITs and beta ITs you can compute. Now remember what is the next step in the algorithm? You want to find out what are the best possible paths, or what are the probabilities in various paths. That's what we intended by doing this alpha and beta. Let us see how exactly we can compute these probabilities of various paths. So I want to compute the probabilities of, say, probability x is equal to I given my observation and parameters theta. Also I want to compute xt is equal to I and xt plus 1 is equal to j given y and theta. I want to compute both of this. So if I can compute both of this, I can compute all the parameters. I can compute my transition probabilities using that. I can compute my initial probabilities using that by taking t is equal to 1, and I can also compute my emission probabilities. So now my problem is, once I have computed alpha and beta, can I compute these probabilities? Okay. So that is what we will see next. So I am giving these some names. So firstly I have this gamma IT that gives me the probability that at tth point the state is I given my observations y and theta parameters. And similarly I have zeta ijt, that is probability that at tth point I have a state I, t plus 1 point I have a state j given y and theta. So gamma IT is written in terms of multiplication of alpha IT and beta IT, okay, divided by summation over all possible sigma j, alpha jt and beta jt over all possible j's. So now, how do we actually come up with this equation of gamma it and zeta ijt? Let us look at it. Okay. So here, I want to compute probability xt given xt is equal to I given y and theta. So now, I will compute it using probability xt is equal to I y given theta divided by probability y given theta. Okay, this is simple conditional rule. Okay, so if you forget theta, this is nothing but xt is equal to y given y is xt is equal to y divided by probability y. Okay, this is simple the conditional probability rule. Now, this one I am writing as summation j is equal to 1 over n, j is equal to 1 to n, probability xt is equal to j y given theta. Okay, so now you can see the symmetry in this equation. Now what I have to show that alpha it times beta it is probability xt is equal to y given theta, and that is very easy, because what is alpha it? This is probability y1 to yt and xt is equal to y. What is beta it? Probability of yt plus 1 to y capital T, and now xt is equal to y is already given for beta, and this is given my parameters theta. Okay, and this is what we are seeing here. This is my alpha it times beta it, and this is marginalizing over all possible states at time point t. So this will be sigma j is equal to 1 to n alpha jt beta jt. So this gives me the equation for gamma it. Similarly, you can see for zeta ijt, that is probability of xt is equal to y, xt plus 1 is equal to j, y given y and theta. So in the same way, you can write it as probability xt is equal to I, xt plus 1 is equal to j, y given theta divided by probability y given theta that will marginalize over all possible I and j. Okay, and you will say probability xt is equal to I, xt plus 1 is equal to j, y given theta for all possible values of I and j. Now what we have to show that is that this is actually this formula. Okay. Now, so what is this? So you are given a state at time point t and time point t plus 1. So what you are actually doing is that you are using the forward procedure from y1 to yt, and you will also get the state at state I at time point t, and you will use the backward procedure because you are given the state at time t plus 1 state j, backward procedure for from yt plus 2 up to y capital T. Okay. So this is what is captured in alpha it, and this is captured condition on j in beta jt plus 1. Then you will compute the probability of transition from I to j, that is aij. Okay, and yt plus 1 given j, that is your bj yt plus 1. Okay. So this equation is nothing but probability of xt is equal to y, xt plus 1 is equal to j, y given theta. This whole sequence is there, and these two states are also there. And similarly, you can see for the for here. This is over all the possible values of I and j. Okay. So I hope this is clear that once I have computed all the possible alpha and beta, and the parameters are, the previous parameters are there, we can compute these gamma I teach and zeta I j teach, that are probability of state at a given time and a sequence I and j at time t and t plus 1. Okay. This we can compute using alpha and beta. Now coming to the last part, that is, once I have computed some probabilities over my possible state paths, how do I estimate my parameters again? Okay, I have started with some initial parameters, computed this, now I want to re-estimate my parameters theta. So how do I do that? So now I have to estimate my pi I, aij and bi vk. So how do I estimate this? Pi I is probability of seeing the state I at time 1. So now from these parameters, which one can give me this value? Probability that x1 is equal to I. This I can get from gamma I1. Okay, that can give me my pi I. Yes, probability that at x1 is I. So this is to estimate my pi. Next thing I have to estimate is transition probabilities. Probability of going from state I to state j. Now I have computed this. Okay. So how do I compute my aij? aij would be at all possible times, how many times you are having the sequence I and j. So this will be summation over t zeta ij t. Okay, zeta ij t is I followed by j, divide by over all the times when you are seeing this t. Okay. So when you are seeing the state I, and this you can compute using your gamma I. So that is summation over t gamma I t, and that can give me my aij. All the possible cases where all the probabilities of I and j occurring together at any point, divide by all the probabilities of I occurring anywhere. This is my aij. And similarly, how can you compute your bj, say vk? That is, at state j you are emitting vk. How can you estimate that? So for that you have to find out whenever you are in state j, is the observation actually vk? How many times you are in state j, where the observation is vk, divide by number of times you are in state j. Okay. So this is, so here the denominator is eg, that is number of times you are. So this is pj vk, number of times you are in state j. So this is gamma j t. Numerator, number of times or the probability that you are in state j times the observation is actually vk. Okay. Now, so at time t the observation is small yt. Okay. So I can use some sort of a simple notation or indicator function, 1 vk is equal to yt. So indicator function. Okay. What is indicator function? So 1 vk is equal to yt will be 1 if vk is actually yt and 0 otherwise. This will be my indicator function. So now whenever, if vk is yt, whenever I have observed yt, I will add it, otherwise it will be 0, and this will give me the emission probabilities. So I could estimate my pi I Eij as well as Bjvk using this zeta ij and gamma I, which I computed using my forward backward probabilities. And this is one complete pass of this algorithm. Okay. Now I have these parameters. I'll plug these again to compute alphas and betas, again compute my gamma and zetas, and again estimate the parameters until it converges. Okay. And this is the Baum-Welch algorithm for learning the parameters of HMM when the labeled dataset is not available. So this gives you a very nice handle on HMMs. So you can apply HMMs when you have the labeled dataset very easily by learning the parameters directly from MLEach, maximum likelihood estimate, and using bit decoding. But even if you get a new problem or a new language for which you have to compute part-of-speech tags, but you do not have the labels, you can use this Baum-Welch algorithm to estimate the parameters of HMM and then use bit decoding to actually, given a new sentence, find that part-of-speech tag sequence. So, and you can use that for any other sequence labeling task. So this completes our discussions on HMMs that were one of the very popular models for this part-of-speech tagging and many other sequence labeling tasks. But they have certain limitations, and that's what we will discuss next. Then that what are these limitations and how do some other models. So we will go to now some discriminative classifiers like maximum entropy models. They get rid of these limitations. So this is for HMMs. And let's look at maximum entropy models in the next lecture.